All right, thank you all for coming. Welcome to Origin Seminar for October 7th. Today we are very pleased to have Kamber Schwarz. Many of you probably know her already. Kamber was an undergrad here at the U of A in physics and astronomy, working with Nancy Shirley. She then went on to the University of Michigan for her PhD, where she worked with Ted Bergen. After which she was a Sagan Fellow here at LPL back in Tucson. She is now a postdoc at the Max Planck Institute for Astrophysics in Heidelberg.
All right. Stand up because it feels weird to get to talk while sitting. Okay, so today I'm going to tell you all about some work that I've been doing at MPIA, looking at MIRI MRS observations of protoplanetary disks. And this is work that I've been doing as part of the MINDS GTO team. So before we get into the science, just a quick reminder for everyone, when we're looking at protoplanetary disks, different wavelengths probe different physical locations in the disk. And that is because the part of the disk that is closer to the central star and closer to the disk surface is going to be hotter. So if you're using, say, ALMA at millimeter wavelengths, you're going to be probing sort of the outer 10 to several hundreds of AU. You're going to be looking at low energy rotational lines of molecules, and you're going to be probing the millimeter midplane dust. If you are looking in the infrared, then you're going to be looking at scales of a few AU to a few tenths of an AU. You're going to be looking at the much hotter energetic lines. So these are your rotational and vibrationally excited lines. And you're going to be looking at the smaller dust grains. And then if you go into, say, the optical or the very near IR, and you look at scattered light, you're really getting the very, very small micron, submicron size grains at the surface of the disk. So when we look at protoplanetary disks with ALMA, particularly at their molecules, the one that's easiest to look at is carbon monoxide. And what we found is that a lot of disks are underabundant in CO gas in the outer tens to hundreds of AU. So we have a couple of examples here showing the depletion factor with respect to ISM as a function of disk radius. However, as we move inside the CO snow line, where the disk is warm enough for the CO ice to become CO gas, we start to see this increase in the amount of CO gas, particularly around massive stars where the disk is hotter and the CO snow line is farther out. And so what our models predict to interpret these sort of observations is that the carbon and oxygen are freezing out into ices in the outer disk, and then these icy grains are going to drift inwards, and then once they pass different snow lines, they will enrich the gas at small radii. And so one of the questions that we were really interested in answering with the launch of JWST was if we see excess carbon and oxygen in the hot inner regions of protoplanetary disks. Now, already with Spitzer, we saw some hints of this. There were surveys which showed that there was this anti-correlation between the water to carbon-bearing species ratio with respect to the size of the dust disk. And then when you correct for the correlation between molecular luminosity and stellar luminosity, it turns out that the strongest correlation was between hot water vapor and the size of your disk, with smaller disks having stronger water emission. And the interpretation of this from Vanzati et al. 2020 was that this was evidence of that icy drift that I was talking about. So the idea is that if you have a disk with a small dust radius, your icy pebbles have efficiently drifted into the inner disk and evaporated their water. If you have a large disk with this dust ring substructure, then you'll find that you have ices trapped in your pressure bumps caused by these dust rings, and you have a lower abundance of water vapor. And then when you have disks where you have a clearing at the smallest radii of the disk, then you have both inner disk depletion from the disk being cleared, and you have the ice trapped in the outer rings, and you have an even lower water abundance, okay? So this is what we were thinking we were going to see with JWST. Some of the first results from the JDisks collaboration looked at water spectra with JWST from 2 disks with small dust radii and 2 disks with large dust radii. And with the improved spectral resolution of JWST, not only were they able to measure the amount of water, but they were able to separate out individual water lines and tell which ones were coming from hot gas and which ones were coming from cold gas. And what they found is in this little subsample of 4, there was excess cold water emission, so emission from cooler water gas in these small disks. However, just a couple of weeks ago, they released a follow-up paper that increased the sample from 4 to 25. And some of the disks still follow that correlation, but there's really a very large spread. So there's something else going on besides just icy grains drifting inwards and increasing the water in your disk. Okay, so the program that I'm going to be talking about today is the MINES program. This is the European GTO program for MIRI with protoplanetary disks, and it stands for the MIRI Mid-Infrared Disk Survey. Our team is shown here. And so this is a survey looking at 51 protoplanetary disks with MIRI MRS. We also have near-spec spectra for a couple of systems, MIRI coronagraphic imaging of TW Hydra, and near-cam imaging of PDS-70. This is a high signal-to-noise survey that is led by Thomas Henning at MPIA. We're mostly looking at disks around T Tauri stars, so these are like solar mass-ish stars. But we also have a few very low mass stars, a couple of high mass stars, and some young gas-rich debris disks. If you want to know more about the sample statistics and the goals of the survey, we have 2 review papers, Kemp et al. 2023 and Henning et al. 2024, which also has our results for TW Hydra, so don't sleep on that. And then some of the first results from this survey is that for T Tauri disks, we are detecting emission from water lines, from HCN and C2H2 sometimes. And for disks around very low mass stars, we very, very rarely detect water. The HCN is very weak, but we see very strong C2H2 as well as other more complex hydrocarbon emission. That's not too surprising. This is consistent with the trends that we were already starting to see with Spitzer. So today I'm going to talk about the source that I have been working on. This is SY Cha. This is a T Tauri disk, so 0.7 solar mass star, moderate inclination, 180 parsecs away. And if we look at the millimeter dust as observed with ALMA, you can see that this looks like a transition disk. So we've got a ring of dust at about 100 AU, a very large cavity, and then we have an unresolved inner disk that is less than 3 AU in radius. However, if we look at the gas that we saw with ALMAs, this is CO, you can see that we do not have a cavity in the CO gas. So if you can see the black line here, that's tracing out the dust ring, and you can see that we still have a very gas-rich dust cavity. This source has also been observed with sphere in H and K band. So this is looking at the scattered light disk surface. And if you look at the polarized H band observations, we actually see some asymmetries in this emission. So once again, this oval is showing you the dust ring in the ALMA image, and we have sort of this like clump and arc feature. We're not entirely sure what causes this yet. There are follow-up observations being done. So that's sort of like the overview of what SY-CHA looks like. It was also previously observed with Spitzer at in both its low resolution mode and in the Spitzer high resolution mode. And then we have our MIRI MRS spectrum. And here, pretty much every single spike that you see in this spectrum is a gas line. So with the improved resolution of MIRI, we're getting a much more detailed view than we've ever had before at these wavelengths. Okay, so in my paper that was published at the beginning of this year, we went through and we tried to characterize all of these gas lines that we see. And so to do this, we subtracted off the continuum within a specific wavelength chunk. And then we used these slab models where we basically just picked a single temperature and a single column density and ran through a bunch of different options until we were able to get a good match to the emission that we see. We did this one molecule at a time and limited ourselves to wavelength ranges where we didn't think there would be a lot of other molecular emission. So this is just an example of what we did for water at our short wavelength range. And then once we fit the water, we moved on to the second species. This is the CO that we detected in this region. And then we get a total spectrum for that area, and that gives us an idea of the temperature and the abundance of that gas. And actually, this is the first detection of mid-IR CO in this source. This is something that we were not able to see with Spitzer. Okay, so we did this for a bunch of different wavelength ranges. And in addition to the first detection of CO in this source, we also have the first mid-IR detection of OH. And then if we look at this wavelength range from about 13 to 15 microns, we see a lot of different molecules here. We see a strong CO2 emission at around 15 microns. We see HCN emission, and we see water emission. Now that's interesting because usually when we look at these disks with JWST, we see either strong water emission or strong emission from carbon-bearing species. An interesting source to compare this to is PDS-70. This is work that was led by my fellow postdoc, Julia Parati at MPIA. And PDS-70 is a disk that in ALMA looks a lot like SY-CHA. We've got an outer ring, an inner disk. A couple differences are PDS-70 B and C. These are massive, actively accreting planets within the cavity. And when we looked at this source with JWST, we found a bunch of water lines in the inner disk. This is the first detection of water in the inner disk of a planet hosting system. Really exciting. Okay, so this is the full MIRI MRS spectrum of PDS-70. And if we now compare that to the MIRI spectrum of SY-CHA, scaled to the same distance, you can see that the inner disk gas emission is way stronger in SY-CHA compared to PDS-70. Now, these are like superficially similar disks. The stellar mass and the inclination of the disk are very similar, but it's not really a fair comparison. So SY-CHA has a much smaller disk, inner disk compared to PDS-70. It's about 2 million years younger. But despite those differences, we find that the water in these two disks has similar temperature, so it should be emitting from about the same region, but we have a much higher column of water in SY-CHA compared to PDS-70. Okay, so in fact, SY-CHA looks a lot less like a disk like PDS-70 and more like this disk, SC98, which was work that was led by Donnie Gossman in the MINDS collaboration, where we do not have this large cavity in the dust, but we have very strong water lines. So Because the SY-CHA inner disk looks a lot more like the inner disk for a full disk without a large cavity, this tells us that whatever is opening up this gap that we see in the millimeter continuum is not blocking gas from reaching the inner disk. So if we look at this cartoon explanation from the Banzati et al. 2020 paper, we see that SY-CHA is one of these disks that bucks this simple trend. We have a dust ring that should be providing a block for the icy dust grains from drifting inwards, but we have a very water-rich inner disk. Okay, that actually shouldn't have surprised us that much, because earlier I said that when we look at the CO gas with ALMA, we see that it fills this dust cavity. And if we once again compare to PDS-70, here we have the same CO observations, or the same CO molecules, transitions, in PDS-70 versus SY-CHA. And you can clearly see that in PDS-70, these massive planets are doing a really good job of clearing out the gas. And that's not what we see in SY-CHA. Okay. Now, that's, yeah.
Sorry, did you talk about the mass accretion rates? Are they different or?
Gosh, I talk about the mass accretion rate of PDS-70, no, of SY-CHA later. They're both low. I don't remember exactly what PDS-70 is. Yeah. Okay. Okay, now when it comes to clearing out dust versus clearing out gas, it turns out that the physical mechanisms are different. So to get a dust cavity, that happens when your dust experiences a pressure bump relative to the gas, okay? But gas depletion, that only happens when you have either accretion or some mechanism that is transferring angular momentum. Now, it could be that the cavity in SY-CHA has planets that are less massive than the PDS-70 planets and sort of hit this sweet spot where they're able to create this pressure bump for the dust, but they are not able to clear away the gas. And that would be really interesting, because that would imply that the composition of your inner disk doesn't just, yeah.
Sorry, do we know if there's a planet in the? That's why.
We haven't detected one yet. There wasn't any clear signs in the sphere imaging, but there was that like weird kind of clump arc asymmetry. So like there's something going on, but we haven't definitively been able to say if there's a planet or not. If they were as massive as the PDS-70 planets, we wouldn't see them. So maybe it's planets, and maybe the composition of your inner disk doesn't just depend on the presence of massive planets, but the exact mass of those planets, which is interesting. But there's lots of ways you can open up a cavity, and it could be that even though PDS-70 and SY-CHA look very similar, the mechanisms that form them are different. TBD. Okay. Also, like I mentioned, this was previously observed with Spitzer. So if we look at the 3 Spitzer epoch observations of PDS-70, and then we look at our MIRI data, we find that the continuum in this source is highly variable. And this variability exceeds our uncertainty on the 2 telescopes. We were really surprised by this. We shouldn't have been, because Catherine Espelot pointed out back in 2011 that transition disks are known to be highly variable in the mid-IR. And what's happening here is that you have a change in geometry of the inner disk, which is going to affect how it's heated, and that's going to change the shape of your continuum. Now, because we saw this large continuum variability, I also wanted to look to see if the gas lines were variable. So what I did was I took the MIRI data shown in this dark purple, degraded it to the resolution of the high resolution Spitzer observations, and then compared the integrated line fluxes for C2H, HCN, CO2, and a couple of the water lines. And if you just look at these spectra, it seems like so obvious that the flux of, say, your C2H2 line is changing. However, if you actually propagate through the uncertainties on these different observations, this variation is actually within the observational uncertainty. So we would really need follow-up observations with JWST to confirm whether or not the line flux is also varying. I do want to point out that we are not the only people who have found variable line fluxes. Another group also saw line variability in the disk AS209. Okay, and then speaking of C2H2, in our paper, we report the C2H2 as a tentative detection. This is our best fit after subtracting off all the other line emission in that area. It was previously reported as a detection based on Spitzer data, but it's not clear if this feature is actually due to stronger C2H2 or if it's due to blending with other lines. Okay, so that was Schwarz et al. 2024, looking at all of the inner disk emission that we saw in the spectrum. But I actually didn't talk about any of the bright lines that I have labeled on this spectrum. And that's because in that first paper, we assumed that all of our emission was coming from the unresolved inner disk. So if you opened up the Fitts cube and you looked at the line emission from, say, CO2, it looks like an unresolved blob with 6 spikes, which shows you that that's the PSF of JWST. However, if we look at one of these, say, H2 lines, it looks not like that. And so here we're actually spatially resolving the molecular hydrogen emission. And if you look at the neon 2, hopefully I can convince you that this right here is in fact resolved emission and not just a little bit of noise. So as I know some of you in this room know, Ilaria recently on Friday had a paper published in Nature Astronomy where she saw spatially resolved tracers of outflows using NIRSpec in 4 disks. So we have an H2N and an iron 2 jet coming off of this protoplanetary disk. I just wanted to mention that. I'm not trying to make any comparisons or anything. Okay, so let's look at all of our H2 lines and let's try to clean up the images a little bit. So to make these images, what we did was we used the continuum in the channels adjacent to the H2 lines to subtract off both the continuum and the PSF. And then we can sharpen these images using a Lucy-Richardson deconvolution. And when we do that, we find that of the 8 H2 lines that we detect in our MIRI data, 5 of them appear to be spatially extended, mostly on the near side of the disk, though maybe you can believe that this blob over here is the far side of the disk and not just noise. Okay, so we've got this lovely spatially extended emission, and now the question is, what is it? Is this a wind? Is this the surface of the disk? Is this a jet? We can compare, just like by eye, the morphology of our H2 emission to our midplane dust and to our scatter light disk surface. And hopefully you can see that the opening angle of our H2 emission is above the scattered light disk surface. So we don't think that this is the surface of the disk. We think that this is likely some kind of outflow. We can then characterize the opening angle of this outflow by tracing the brightest pixel at a given offset and then fitting a line. And we find an opening angle, depending on which transition we look at, between 64 degrees and 48 degrees. And that is too wide to be a jet, which is going to be much more collimated. So this is looking like a molecular disk wind. We can further characterize it by using rotation diagrams. So basically, we just sum up the flux within a 2 arcsecond aperture for our 8 different transitions. And then we can fit a line where the slope of the line is related to the temperature of the gas and the y-intercept is related to the column density. Now, in this particular case, we clearly do not have a straight line, so we have to have at least two components. I'm going to call these the hot component and the warm component. So our hot component has a temperature of around 1700 Kelvin. So perhaps that is a hot outflow. And then we have our warm component of about 600 Kelvin. And that is what we would expect the temperature to be for H2 emission at the disk surface, as previously shown by Riccardo Franceschi for another disk in the mine sample where we do not see this extended emission. Now we can test this idea that we've got like an outflow in a disk surface by separating out the emission within the inner 5 arc seconds and the extended emission. And then when we do that, in the inner region, we still have a hot component, slightly cooler at 1300 Kelvin. And that's mostly because we're not including a bunch of noise out here for the lines that are not extended. And we have our warm component. Okay, so it looks like that's a disk surface. And then if we look at only the extended emission, we have only the hot component. So it seems like disk surface plus outflow is the correct interpretation. We can then compare this to other observations of extended H2 emission in the literature. And if we compare the combination of our opening angles and our temperatures, then they are similar to what we've seen both for the ground vibrational state like we're seeing and for some of the near spec observations of the first vibrationally excited state, also what we've seen all the way back in 2008. So these papers interpreted their H2 emission as being from a disk wind. What we are seeing is similar. So I'm going to go ahead and say that we have a polychromatic disk wind in SY chalk. We can now calculate the disk mass loss rate. So remember, we got our H2 abundance from the y-intercept in our rotation diagram. It corresponds to an H2 mass of 4 plus or minus 3, 10 to the negative 7 solar masses. We can assume a wind velocity. Our spectral resolution doesn't actually like spectrally resolve the lines, but a typical assumed wind velocity is 10 kilometers per second. We can measure the extent of the emission, and that gives us a molecular wind mass loss rate of about 10 to the minus 11 solar masses per year. That's about an order of magnitude lower than the accretion rate onto the central star, and it's significantly lower than a lot of the wind mass loss rates in the literature. Now, this is a lower limit on the mass loss rate because we're only looking at the molecular H2. However, it's low. Perhaps this, yeah.
Sorry to interrupt, Kamber. I have a quick question. Is there any chance any of the H2 emission because they're getting optically thick, or are you in a regime where that could ever be a possibility? When you did a rotation diagram, assuming everything's optically thin and derived column densities from an optically thin assumption, is it ever possible that you can get enough H2 long line set to be thick in these rotation lines that you're seeing?
Theoretically, it's possible, but we did go back and do an assumption or look at whether or not our assumption of like LTE optically thin was valid. And based on some wind models that Andrew Selleck has been running, this does seem to be optically thin emission in LTE, like the temperature and everything is consistent with that. Yeah. Okay, so this low wind mass loss rate could be due to the evolution of the source. It could be that we are seeing a disk that's moving from being a gas-rich transition disk to a gas-poor transition disk. If we once again compare to PDS-70, in PDS-70, there is a disk wind that has been observed in the optical in 01. But if we look at the MIRI data with JWST, we do not see a disk wind, and that is work that's being done by a master's student at MPIA. So it could be that this is just a less evolved version of the transition disk that we're seeing in PDS-70. Okay, and then finally, I said that I wanted to convince you that that blob in Neon 2 was really extended emission. So these are the channel maps for the Neon 2, done in the same way as we did for the H2. You can see that we did not do as good a job of subtracting off the PSF. And we think that that's because there's a strong component of Neon 2 emission that's unresolved. However, while we did not have the spectral resolution to spectrally resolve the H2 lines, we do clearly see a velocity offset for the Neon 2. And I'm going to claim that we see a blue shifted component, and then on the other side of the source, we see a red shifted component. So I'm going to say that because this is high velocity emission that appears much more collimated than the H2 emission, and that we have spatially separated blue and red lobes, that this is a jet. I would love to tell you more about this jet. Unfortunately, we only have the one line. We do see other forbidden lines in our spectrum. However, none of them are spatially resolved. So I can't really tell you anything about like the electron density in this jet. All right, so that is the MIRI view of the protoplanetary disk S by Cha. In the first paper, we focused on the emission from the central region, and we found that the inner disk is very line-rich despite this millimeter ring. The continuum and perhaps the lines are variable with time. In the follow-up paper, we found a jet in Neon 2 and 5 spatially extended H2 lines consisting of a hot disk wind component and a cooler disk surface. We find a low mass loss rate from this wind relative both to the stellar accretion rate and to winds in other sources, which is perhaps due to a disk that is transitioning from being gas-rich to gas-poor. All right, thank you, everyone.
I'm curious, a very nice talk. So I'm curious about the height of the wind compared to the scatter light surface.
Yeah.
Is there any work that tried to derive the height of the scatter light surface?
There is. So the Gensky et al. 2024 paper did trace out the height of the scattered light surface, and the H2 that we're seeing is significantly above the scattered light for a given radius.
Hey, very nice talk. I'm wondering why you didn't see the extended emission of other forbidden lines. Could it be that the data had too low sensitivity?
Yeah, absolutely. So don't know if I can easily go back, but if we look at the actual spectrum, right? The Neon 2 line where we see the extended emission is by far the strongest forbidden line that we see. So it could be that they are also extended, we just didn't have the sensitivity to detect them.
Yeah, go ahead.
For next Kamber. So I was wondering, since you have very large cavity disk, when you do your PSF subtraction, do you still see medium-free emission in the outer part of the disk? So in that case, we can get spatial resolved spectrum to compare with.
Yeah, that's a good question. So because the way that we did the PSF subtraction was subtracting off the PSF and the dust continuum at the same time, like that method didn't really let us check for that. But I will say that just like scrolling through the data cubes, nothing jumped out to me as being like extended emission beyond the H2 and the Neon 2. So maybe if someone went back and did it more carefully, they could see something like that.
Yeah, thanks. It was very nice. Couple of questions. So first of all, I was curious if you detected any iron lines, because iron is also very good tracers of jets. And there are a couple of transitions around between 5 and 6 micron and also at longer wave.
Yeah, so I did check, and if we have any iron lines, they're weak enough that they're being masked by the water lines at those wavelengths. So maybe if we went to like near spec, we could look for some iron lines.
And the other thing is that, can you bring up again the comparison between the mass accretion rate and the wind mass loss rate?
Yes.
Okay, so it's
A little bit more than an order of magnitude, but then, I mean, our mass loss rate for the H2 is pretty uncertain, right? So I wouldn't focus on this bit, I'd focus on this bit.
yeah, I mean, I was just noticing that the velocity that you assumed is more for a photoevaporative wind. But I mean, if this is an MHD wind, it could be 5 times larger, for instance. So that would bring up your,
Yeah, because it would scale
Yeah.
linearly. That is correct.
so it might help.
Yeah, it could be higher than this.
There was a question on,
Yeah, so there are two questions online. So Joan Najida says, great talk, fascinating results. What is the expected fraction of H2 to H1 in the wind? So molecular to atomic hydrogen in the wind. If it's low, could the wind mass loss rate be similar to the disk accretion rate?
Yes. Hi, Joan. My understanding is that you would expect most of the mass in the wind to be atomic, so then it could be similar. And the reason that people are interested in this is because, and please correct me if I'm wrong, Alari, because you are the expert in the room, but MHD-driven winds are correlated to stellar accretion, but photoevaporative winds are not. Correct?
not necessarily, yeah.
Okay.
Yeah.
Okay, yeah.
Second question from Naman Bajaj. Great talk and beautiful images. Two questions. One, since you deconvolve using the nearby continuum, is it possible for the continuum to be extended and that is affecting the H2 emission? And second question, how does the H2 opening angle compare with other H2 winds and other objects? Does it have anything to do with MHD versus photoevaporative origin of winds?
Yes, okay. So first question, we don't see, even like before I do the PSF subtraction, kind of like I was talking about, next question, continuum. Whereas say in the Arulanantham paper, I believe that these contours are for the dust continuum. We don't see that in the source. Our opening angle is pretty consistent with the opening angles that are seen in the sources on this slide, as well as with the opening angles that are reported in Ilaria's recent paper, looking at near spec. I think 65 is a little bit wider than has mostly been reported, but that's also for one of the lines where the signal to noise was not so great. You could try to trace back these angles to a launch radius in the disk, and see if that can tell you whether or not you're in the right distance from the central star for it to be photoevaporative. I do not trust these derived angles enough to make that extrapolation. I think that we would need like higher resolution observations, or I think the best way to determine whether or not these are MHD or photoevaporative winds is to get higher spectral resolution observations so that we can get the velocity of this emission.
Are there any other questions in the room?
Ask another one. Yes. So I was wondering about the water detection in this disk. So I feel like, how can we determine if the dust trap is real weak or strong? If there is small grains that can bring water ice, like the PSM disk. So is the small grain carried ice enough to explain a water column in your system?
Yeah, so I think you would need to ask someone who does like dust drift modeling for that. I think the real question is, which I don't have an answer to, do we have an inner disk that is being continuously fed by the inward drift of very small grains? Or do we have a disk where drift is now blocked by that ring, but it happened pretty recently and we haven't stripped away the gas from the inner disk yet? And that, once again, if we could figure out the origin of these disk winds, could help us answer that.
Kamber, sorry, back to that. So do you see in the water both the hot, warm and cool component? So there is also a cold
Yeah, so yes,
that
so
could be related to the
yeah,
pebbles.
so the way that most modeling of water with MIRI spectra works now is you have 2 to 3 water components with different temperatures that you fit simultaneously, because you have lines that have different upper state energies that are like right next to each other. But there is a general trend of like more lines for the hot water at shorter wavelengths. What I did in this paper, which was a little bit before that became standard practice, was I just fit like a chunk of wavelength range at a time. But even when you're doing that, you can see that the best fit with wavelength changes with temperature. Yeah, so we do have multiple water temperature components.
Are there any more questions online? And you can either type into the chat or raise your hand. Are there any more questions in the room?
I have another question. I'm sorry, this is very interesting. So with your, you have these multiple H2 lines. So do you see gradual opening of the wind as you go to lower energies?
Well, so originally we thought that we saw the opposite of that.
Yeah. But no.
But right, so this is the higher energy, this is the lower energy. We thought we saw a trend where higher energy had a wider opening angle and lower energy had a narrower opening angle. But then when I redid the analysis, it's just kind of like all over the place. So
You all know what I'm gonna ask.
No.
All right, well, if there are no more questions in the room or online, let's thank Kamber for an excellent talk.